I was actually about to park you in front of this for 2 minutes because I've got a task for you to do actually, and also because I need to do a very small amount of faffing. Right, you've got 5 pictures of Saturn here, everyone. 2 minutes to think about what year were those pictures taken, do you reckon? So we've got a very detailed, colourful image. We've got a beautiful grainy black and white image. We've got a pretty clear, maybe not quite as colourful image. Completely black and white image with not really any detail at all, just the shapes, and a kind of creamy yellowy browny one. 5 different images. What year do you think they were produced? 1909, 1884, 1973, 2008, 2018. I'm going to faff for what now, like, I don't know, 1.5 minutes, and then we'll get started. Don't really need any. Oh no! Oh no! Oh no! Okay, make that. No, sorry, that was the sound I make when I spill water on electrical equipment, which is why you should always keep your house tidy, children. It's fine. It wasn't very much water or very much electrical equipment. Oh, some paper is getting wet. Is it important paper? No, it's not actually. In fact, it can just be used to mop it up. Brilliant. It's all come together and I've learned nothing. Right. What do I need? I need a tea towel now. And yeah, okay, right. 2 minutes of faffing and then I'll be back and I'll flip you around. Okay, my Science Alliance chums. Right, I've got my coffee. I've got my favourite cosy little cardigan. I've got my tea towel. Move that over there. Just plop that on there. I was just about to tidy up this office anyway. And I need some A4 paper. Surely I don't need pristine. No, I don't think I do. Oh no, here's some. Great. I've always got paper around from story time. I'll use that. Paper, scissors, sellotape, and a CD. Oh, it's a lovely activity today. I sort of made this one up. I mean, I didn't. This is a really common thing to do if you're doing like science activity, kids. But all the ones that I could find online were a bit too complicated. It was that sort of activity where it's like a kid's activity, but then every stage is get an adult to do this for you. Ask an adult for help with this bit. So I tried to make it that you didn't need anyone's help. If you're like me and you don't accept help. Right. That's dry. Not there, not there, not there. Yeah, bit of string as well. I just need a CD. Get that from my stack of old CDs. Oh, yes. Awesome. Right, we can get going. With deepest apologies, as usual, for being late. If you're new, it's like this every time. I don't always spill liquid, but apart from that, it's exactly the same as this every time. Right, I'm flipping you around. I'm going to unplug you. There we go. Oh, you see, there's more people watching now than there were before. I've learned nothing. You guys reward me for faffing. Oh, it's terrifying. Shut the door. There. Right. Let's go. Let's start in the lesson. Hello, Science Alliance. My name is Lara. This is Theory of Science. I'm teaching you astronomy, which is good because I am actually trained to teach physics up to A level. I basically busk science lessons into the internet. So if you're new, at the end of this lesson, I will tell you how you can kind of put money in my digital hat. And that is literally the only way that anyone in my family gets paid now, is from me busking science lessons. What a wonderful time to be alive. Right, we're learning about exoplanets. We're going to do a very cool activity. While I'm telling you about exoplanets to sort of start off, can you please, if you're doing the activity with me, cut about 8 bits of sellotape, about the length of a finger. We're basically just going to stick 2 bits of A4 paper together and then roll them up and then stick that together. So, I don't know, is that clear? 8 bits of sellotape. I'm doing that off screen, which is rubbish telly, sorry, but you're going to have to put them on the edge of a table, aren't you? Please don't put them on the edge of like a piano stool or a guitar. If you haven't got anywhere to put your sellotape, go to the kitchen and get a pan. You've got time. Put them on the edge of a pan. Right, exoplanets. This is our 3rd lesson, but you don't need to have seen the other lessons. So an exoplanet is any planet that is not in our solar system. So I thought, well, some of you might need a bit of a recap on what our solar system is. So let's talk about that, okay? 1, 2, 3, 4, 5, 6, 7, 8. 1 for luck. Fine. Here we go. You ready for my amazing PowerPoint special effect? Here is the sun, right? You know the sun, yeah? The sun, and the sun has got 8 planets. Don't get on me about Pluto. Pluto's a dwarf planet. 8 planets going around the sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So that is basically our solar system. It's all the planets in our solar system. So it's a bit like, stars are a little bit like, the sun's a bit like a pet rabbit, right? If you've got a pet rabbit, you give it a name, don't you? Because it sort of lives with you and you kind of feel like you know it. You wouldn't name like all the wild rabbits in a field. That would be weird. So we live in a group. The sun is just a star, right? It's actually a super boring, run-of-the-mill, average star. And it's in a cluster of loads and loads and loads of stars, which is... It's a lot of words if you don't know this. So here's our sun, all the planets, but the sun is just a super boring star, and it exists in a galaxy of other stars, which is called the Milky Way. Here we go. I got a bit carried away with this bit. So you could think of this as our sun, but it's just a boring star along with loads of other boring stars. Do you know how many stars there are in our galaxy, our group of stars, the Milky Way? There are, oh, come on, Lara. There we go. 100 to 400 billion. Billion! In our Milky Way galaxy. So if you imagine that every single one of those stars has got, not every single one, but if you imagine that most of those stars have got a planet or 2 or 8 orbiting them, that's a lot of other planets, isn't it? A lot of planets that aren't just our 8 planets. There are certainly more planets than there are stars in our galaxy. On average, each star has got well over 1 planet. I mean, we're not even going to talk about, like, our Milky Way galaxy is just one of loads of other galaxies in the universe. It just gets a bit painful for the brain, doesn't it? There's well over, I mean, there could be trillions, but there's well over 200 billion galaxies in the universe. We're not going to think about that. We haven't got direct evidence of any, what you would call, extragalactic planets yet. But we do have quite a lot of evidence for around thousands of exoplanets that are in our group of stars, right? Anything that isn't Mercury, Venus, Earth, Saturn, Jupiter, Mars, Uranus, Neptune. Okay, so we're going to talk about how basically we've got evidence for those, how we have found these other exoplanets. So can you please, if you've finished cutting your sellotape, Can you get a piece of string? It doesn't matter if you're not doing this with me, but it's just a fun. I thought we've got sellotape anyway. Let's multitask. Can you get a piece of string and just tie it around your sellotape? You can do it in a really rubbish way. Don't use a complicated knot or like a shoelace, just whatever you've got. Just a little bit of string and tie it around your sellotape. Which planet in our solar system is your favourite one? Which planet in our solar system is your favourite one? You got one? Stop it. No, it's not. Stop saying Mars or Saturn. It's not, is it? It's Earth. It's obviously Earth is your favourite one. Earth's amazing. Why is Earth amazing? Well, loads of life has evolved to be on Earth. Why has loads of life evolved to be on Earth? It's because it's in like just the right place. It's in what some astronomers call the Goldilocks zone or the habitable zone because it's habitable. It's basically not too hot and it's not too cold. That's why it gets called the Goldilocks zone. It's not Mercury right up close to the sun, very hot, and it's not Neptune really far away from the sun, very cold. Now, I think a lot of you knew that already. What people were really struggling with when I taught this lesson on Facebook was, why is that good to be not too hot or not too cold? Why do we need, if life is going to evolve, why does a planet need to be not too hot or not too cold? I'm doing this to show you that this is what you do. Put the sellotape on a string. Now, a lot of people just really quickly said, well, because it would be too hot or it would be too cold. Like, life couldn't survive. I was like, yeah. But, like, there's really hot bits of Earth, aren't there? Like, you get cacti that have evolved to be in really hot places on Earth. And there's cold places on Earth, like penguins live at the, which one is it? South Pole, isn't it? And they've got special stuff in their blood that makes their feet not freeze because they're just touching ice all day. Like, what is that? Why can't life evolve to be really hot and really cold? It's because of liquid water. It's because, as far as we know, you need liquid water for life to evolve. So Neptune is too far away from the sun and water is just ice. And Mercury is so close to the sun that it just becomes like a gas straight away. It's like trying to keep liquid water in a kettle when it's just on boil all the time. So when we're looking for a habitable zone, we're looking for a planet. If we're looking for like life out in space, we're looking for a rocky planet like Earth, which is just in the right place that you can get liquid water. Okay, let's have a little look at the different methods that astronomers use to find exoplanets. If you've got a bit of sellotape on a string, can you just give it a spin around? I'm holding it up here so that you can see it, so that it's better telly. Don't you do this, because you might put yourself in the face, okay? Be careful, don't hit yourself in the face. Little challenge for you. Can you please spin the sellotape without moving your hand at all? Because if you see here, if I do this, you can see that to get it moving in a circle, I'm moving my hand round in a circle. Can you get it so that your hand isn't moving at all? I mean, you might end up like keeping your hand still but moving your arm. That still counts as moving your hand. That's cheating. Can you not move your hand at all? If you're not doing it, can you tell me if it's possible for me to do it? How do I do it? How do I move that sellotape without moving my hand? So what we'll do is we'll imagine that our hand is the sun and the sellotape is a big planet. Let's say it's a gas giant like Jupiter. This is like not an awful model for what happens. So the answer is you can't. No, you can't. How sort of gravity and orbits work is, oh, I just topped up my pens. This will be exciting. Are you ready? Wait, where's the? Oh, and then I neatly put them back in the drawer. So imagine that you've got a star. Let's do it in orange. Let's make it a star shape, even though they're not a star shape, so that we know that that's a star. If you've got a star and you've got a planet going around it, oh yes, well done me yesterday. what is actually happening is this. So the star's massive, right? The star's got loads of gravity because it's massive. So the star is pulling on the planet. When stuff orbits stuff, what's actually happening is the planet is constantly falling towards the star, but it keeps missing, really. So the star's pulling on the planet, just like you were pulling on the sellotape to make it go round and round. But just like your hand was wobbling a little bit, the planet is also massive. It's got mass, so it's also got gravity, and it pulls on the star. So the star ends up going kind of to and fro and to and fro. Why? How on earth are you going to? Why would that mean that you could look into space and see that thing? Well, the proper name for this is the radial velocity method. There may or may not be a quiz about this at the end. There is. I've come up with a new quiz. I'm very pleased with it. Velocity. Radial means, you know, like the radius of a circle, kind of the distance from a circle to the middle to the edge. And velocity means speed. So this method has to do with how fast the star is moving. In the first lesson, we had a look at things like this. We were looking at how light is a wave, and different coloured lights are sort of slightly different length waves, right? So red light is quite a long wave like this, whereas violet and blue light is quite a squished up wave like this. So what happens is, with the wobble method or the radial velocity method, the star moves like this. And when it's giving off light, if it's coming towards us, the light gets a bit squished. So let's say it's supposed to be green light, the one in the middle, like the medium length light. If it's coming towards us, the green light gets squished and looks a little bit more blue, like a little bit more bunched up, like blue light. And if it's going away from us, then the green light would get a bit stretched, get a bit longer, and it would look a little bit more red. So astronomers can look at this wobbling star and go, oh, that's not the colour light that I was expecting to come from a star like that. Oh, that's definitely not the colour light I was expecting to come from a star like that. And they know it's wobbling, its radial velocity is changing, and therefore it must be being pulled on by a planet. Right, let's start making our proper thing. You don't need the sellotape anymore, so you can keep the string around it for a bit if you like. Let's stick 2 A4 sheets of paper together, okay? So again, you can do it on a table. I'm going to hold it up to show you. You just overlap the long sides of the bit of paper and then stick it together. That's it. Just put some, I haven't got another arm so I can't show you. Just put some sellotape on that middle bit to stick it together. Yeah, you know what I mean. So the radial velocity method is actually the method that has been used to find the most exoplanets. I can't remember. I knew I'd forget. It's like 80%. I think most of the exoplanets that we've found so far have been found using the wobble method, the radial velocity method. But actually, when I looked it up quite recently, like last week for this lesson, the NASA website is now describing it as the classical method of finding exoplanets, which to me suggests that they think of it as kind of the old-fashioned method. So there are other methods that we use now. So we'll talk about those. Right, I've done that. One bit of my sellotape, I think, was a really old bit that was on my table. So well, why should I apologise to you for having growth sellotape? You're not in the room, it's fine. Stick a bit of paper together like that, okay? I've got a bit spare, so I'll put one on the other side as well. So the other method is called the transit method. The transit method is when a planet is orbiting a star and passes in front of it. I think we maybe better start making our stars the actual kind of shape that stars are. So you've got a bright, bright, bright star. Again, this may or may not be in my little bingo quiz at the end for you. And you've got a planet, there we go, which orbits this star. And at some point, it passes in front of it. Why would astronomers be able to detect that? Why would that be good for astronomers? Well, I'll show you in a graph. It's like a secret fact that people don't usually tell children, that astronomy is just all about graphs. Here we go. The transit method is when this happens. So you get a planet passing in front of the star, and if you study the brightness of the star, what happens is you notice a little dip in the brightness, which is ridiculous. If you imagine that this is like 1,000,000 squares, this star, then the planet would be 100 squares. It's a tiny little dip in the brightness, but it means that it does block some of the light getting to our telescopes, and we can detect this now. So here's what NASA says about the transit method, because it's not enough to just see a dip in brightness. I hadn't really thought about this. the change must be absolutely periodic, right? So it has to happen every time, if you know what I mean. So we're looking for a change in the star's brightness that lasts between 2 to 16 hours, and the dimness happens at the same time each time. It's also got to produce the same change in brightness and last for the same amount of time, which makes sense, doesn't it? Because if you just notice a little dim in brightness and then nothing else, or a dimness and then nothing, and then suddenly some dimness again, it might just be that loads of bits of rock or whatever or comet is passing in front. So it needs to be this kind of regular periodic dimming to know that it's a planet. So that's the transit method, very popular. There is a sort of problem with it to do with angles. Like, you can't always use the transit method to detect a planet. I've said too much. I've made it too obvious. You see what I mean? Can you think of a situation in which you couldn't use the transit method to detect a planet? Oh, thanks NASA, by the way. I've got to credit them for all that information that I just showed you. Can you see it? I'll tell you what, while you're thinking, if you've got your 2 A4 bits of paper, can you roll it up into a tube which is sort of a little bit less narrow than a toilet roll tube? Less narrow? A little bit narrower. A little bit thinner than a toilet roll tube. Like that. Yeah? Like a really rubbish telescope, like a child's telescope. There you go. And then sellotape it. The problem, which is to do with angles, you get what I mean? Yeah, you just roll it up and then you sellotape it. You do get what I mean, don't you? I can move on. Well, it's all very well if this is happening. That would be great if that was the angle that we were looking at that star in space. But what if the planet was orbiting the star like that? Oh no! There's a planet going around that star, but we're not going to be able to tell, are we, using the transit method, because it's never going to pass in front of the star. It's not going to create any dimming. And you do see images where maybe the planet is like the sort of, the angle that we're at is just overlapping a teeny tiny amount. We've got sort of really sensitive equipment now which can sort that out. Okay, while you're making your tube, let's talk about direct imaging, which basically is like the cool method. You know, a couple of weeks ago we talked about light from the moon bouncing off the moon and into our telescopes, and that means like light basically comes from the moon carrying information about the moon, and you can look at the light through a telescope, see the moon. Can't we do that? I mean, light from this star is bouncing off this exoplanet, isn't it? Obviously only a little bit, and this thing is light years away. Like, it has taken light traveling at the speed of light many years to get to our eyes, but still there's a bit of light there. Well, this is why I gave you this little quiz sort of activity at the beginning about Saturn. So I gave you these 5 different images of Saturn, and I said, can you tell me which year they were produced and why? So the first one was the one where there wasn't any detail, it's just black and white. This was made in 1884, and that's as seen from Earth. So that's the first one. The second one is the beautiful grainy black and white smudgy image. That was taken in 1909. I left this in because if you came to the telescope lesson last week, you might know what this means now. Taken from Earth with a 24-inch refractor. Remember refractor telescopes with the lenses? I was trying not to say this image. It just looks 70s, doesn't it? It's just got a real 70s colour scheme going on. Lots of browns and golds. That was 1973. And that one didn't have the Earth's atmosphere to worry about. That was taken from space by the Pioneer 11 spacecraft. And the next one was taken in 2008, again from the spacecraft Cassini. Oh, stunning, isn't it? Oh, it's hard to imagine that's a picture, like an image, but it is a photo. And this one was taken in 2018 by the Hubble Space Telescope. So the odd one out, I said, it's a bit tricky really, was the 1884 one, because that is not actually a photograph, it's a drawing. Oh, sorry. I mean, you could have said the other one was like the only one taken with a camera from Earth or whatever. But yeah, one of them was a drawing. And this, I thought, was quite an interesting thing to talk about, because I've been looking up, let me find it. I've been looking up a lot of exoplanets, obviously, to talk to you about them, and seen a lot of exoplanet news over the last couple of weeks. So I found this and I thought, I wonder what they think about this. So this is from the European Southern Observatory. We talked about the Very Large Telescope last week. So the Very Large Telescope, they've released a press release. So that's where if you make a cool discovery, so that journalists don't have to bother writing their own story, you write a press release to tell everyone what's happened, and the journalists can sort of copy if they want. So their big story is the gravity instrument on the Very Large Telescope breaks new ground in exoplanet imaging. Cutting edge Very Large Telescope instrument reveals details of a storm-racked exoplanet using optical interferometry. Optical interferometry basically means using lots of little telescopes as if it's one big telescope. But it's basically light from the planet getting to telescopes on Earth in this case. Okay, the gravity instrument on ESO's Very Large Telescope has made the first direct observation of an exoplanet using optical blah blah blah. So there you go. And then there's the picture to go with it. Isn't that gorgeous? Wow. And the caption on the image says, "Gravity instrument breaks new ground in exoplanet imaging." And there's the credit. And it's only really, I mean, I think that seems quite a lot of scientific knowledge. If you go here to all the images and you click on the actual image, there's the image that they've used. And like just up here where it says about the image, in this tiny little words, it says artwork. So that's not, the story is about how they've got an amazing new image of this exoplanet, but that is not the image. That is an artist just thinking about what the planet looks like. And we've talked before about how art is really important for science. If you want to get lots of money to make cool discoveries, it's important that people are excited about the work that you're doing. And producing beautiful pictures is a really good way to get people excited. Here's the actual image of the exoplanet that we have. It's still very cool. Here we go. So this is the star HR 8799, and these are exoplanets around the star, and it's E is the one that they were imaging. I mean, it's still awesome, isn't it? But it did make me chuckle. I thought, like, in 40 years' time, people would be looking at that and going, "No, they thought that was cool." Goodness knows, like looking at those Saturn pictures, how quickly we've got the most incredible images where we'll be in a few years' time. It's a really exciting time for exoplanets, actually, because it's all kicking off. This is the... Well, it's sort of a little video. Someone has taken years to put images of this exoplanet together. This, well, four big Jupiters. And if I click on it, it'll start to move. You ready? I think this is the most impressive exoplanet image so far. Everyone was very excited about this. So all these white dots here. I think this is infrared, actually. All these white dots are these huge sort of massive Jupiter-esque planets going around this star here. I don't know how impressive you think that is. Like, that's actually happening somewhere out there. It's pretty amazing. You can see here, this is the years it took to get those images and put them together. Anyway, so look out for direct imaging. It's an exciting time for direct imaging because they're sending a new telescope up in space. Right, we better crack on, actually. What you need to do now is, in fact, I'll show you what we're going to do. I don't usually like spoilers, but I think it'll help you to know which way you have to cut the slit. Sorry, this is a bit wet. Because I just spilled water all over my desk. What we're going to do is cut a slit downwards towards the bottom of your tube, so that we can put a CD in, and then we're going to cut another hole and look through it, and then we're going to see a rainbow. Hopefully. It's going to be amazing. So what you need to make sure you do is, if you get your tube, go about halfway and then go halfway again. So about a quarter of the way down, you need to cut a slit pointing downwards, okay? Towards the bottom, like the bottom quarter of the tube, cut a slit pointing downwards. Here we go. I'll use it on my brand new pristine tube. So careful of your fingers, obviously. Quarter of the way down, cut a slit going downwards like that. About halfway along, I guess. Like that. Pointing downwards. If you've made a mistake, if you've accidentally done it so the slit's pointing upwards, you can just cut it off and start again. You don't really need the tube to be this long. Alright? So slit pointing downwards, you get me? Like that. I've just done it. If you go wrong, just cut it off and start again, because you don't really need the whole tube anyway. Right, yeah. So, direct imaging of exoplanets. There's a new telescope going into space. It's named after NASA's first chief of astronomy. NASA's first chief of astronomy was called Nancy. I know, right? Surprise! What What was Nancy Grace Roman doing being NASA's first chief of astronomy in the 60s and 70s? How on earth did she get that job? Like, women were barely allowed to get degrees at that time in history. Well, as you can imagine, it was incredibly difficult. Her dad was actually a physicist, so I presume that's why she got really into it. I don't know. But basically, everywhere she went, people just kept going, "Oh no, I'm not teaching you. What are you talking about? No, go see that guy." And then that guy would be like, "Oh no." Eventually, someone was really sweet and encouraging to her and said something like, "Oh, I don't usually say that women can do astronomy, but I suppose you might be able to." Anyway, eventually she sort of got quite famous because she did loads of cool stuff, like went around the world giving talks about the stuff that she'd done. And someone came over and said, "Do you know anyone who might want to be chief of astronomy at NASA, because we're setting one up?" And she thought that he meant, "You should go for the job." I don't know whether he did, but anyway, she was like, "Oh yeah, I'll do it." So that's Nancy Grace Roman. They are sending the Nancy Grace Roman telescope into space. I'm holding this so that you can see what I've done. And it's got something cool on it, which means we're going to be able to look at, hopefully, pictures of exoplanets, like in the next few years. Okay, so tell me this. Have you cut your slit? Can we move on if you've cut your slit? You need another hole sort of opposite the slit and then just a little bit higher. So go the top of the slit, go across, and then just a little bit higher, and cut a little diamond out of that. I think that's the easiest way to do it. Again, be careful of your fingers, right? Do get an adult to help you. I should have said that ages ago. Get an adult to do it if you don't usually cut stuff. There you go. So I've got a slit pointing downwards. Keep bending it so that you can see. Slit pointing downwards and a little hole there like that. Right, while you're doing that, I'll tell you why the Nancy Grace Roman telescope is cool. If the sun is in your eyes, so you can't see, imagine you crossing a road and you can't really see the cars because the sun's in your eyes. What do? I'd say do it, but you're probably busy cutting a little hole. What do you do if the sun's in your eyes and you can't see stuff? You do that, don't you? You like shade out the sun from your eyes because there's too much light getting into your eyes. Your eyes are flooded with light, so you can't make out details. You shade your eyes so light from the sun isn't getting into your eyes, so that light from the cars or the trees, the things that you want to be able to see, does get into your eyes and carry that information. Basically, telescopes can have this thing on them that does that, and it's called a coronagraph. And lots of telescopes have chronographs at the moment, like the James Webb telescope has one, but it's a sort of just a kind of rigid thing that doesn't move. The awesome thing about the Nancy Grace Roman telescope, are you okay? Have you cut a slit in it and then cut a little diamond out on the side? And then when you're ready, you can just make it into a tube again. And you should have a slit and a diamond. Right, we need to move on because we need to look through this. The Nancy Grace Roman telescope's got a coronagraph on it, but it's a super cool special coronagraph. It's actually the first active coronagraph in space. It can adapt. So NASA says, I'm not going to pretend to understand any of this. It's a system of masks, prisms, detectors, filters, and self-flexing mirrors. It sounds cooler, doesn't it? For blocking out the glare of stars and directly imaging the planets and disks in orbit around them. Woohoo! All right, watch this space, kids. Here's what an image looks like if it's been taken with a coronagraph. So that's what that circle is with the star in it. This is the exoplanet here. And this is the star TWA7. 111 light years away this exoplanet is. So the coronagraph has blocked out TWA7 so that the light from the exoplanet is more visible. So that's what that image means. Right, shall we use our spectrometer that we have just made? We've made a spectrometer. A spectrometer splits all the colours of, so stick your CD in there. Look through your little hole and hopefully you should see a rainbow. This worked very well on Facebook yesterday and horribly the lesson before that, so we'll see. I've said a few times, white light is made of all the colours of the rainbow. It doesn't have to be, actually. It's not really, but it's a bit like paint mixing. You know how you could get 100 different colours of paint, mix them together and you'd have brown? Or you could just mix like some reds and blues and yellows together and you'd still have brown. So you can just get a few colours of the rainbow and mix them together and it still makes white light. So what a spectrometer does is it looks at the light being given off by a thing and it looks at what colours of light are making it well, it just looks at the colours of light being given off by a thing. Okay, so quite often it would look like a rainbow, but there would be black lines where certain colours were missing. So here's a lovely picture from NASA. Showing what a fluorescent light bulb will look like. A fluorescent light bulb isn't giving off all the colours of the rainbow. There's lots of black bits. It doesn't matter, because when you add the colours that are left together, you still get white light. So hopefully you've made a spectrometer. I say hopefully. Sometimes mine works really well, but it doesn't really allow you to see it. I'm just looking through here and thinking, for some reason I've got a bit of stick it in a different way. I forget I have got 3 spectrometers here now, so I can always use another one. Why isn't that working? But oh, I know. My paper's got a little bit bent on the inside, so it was covering up the CD. I'll show you my fluorescent light in my light bulb, and then I'll show you. Obviously, never look at the sun. We've talked about that. But if you go outside in the daylight, sunlight will go through the tube, and then you can look in that direction. That's the nice thing about these. I'll give it a go. I'll have a look. Some of you won't be doing this activity, so you'll want to see through mine, right? Here we go. So this, I'll just pointing this up at a light bulb in my. I'll just stand on the table. I'm sure that's fine. Kids don't need to do this, right? There we go. See that? So that is the spectrum of colours that my light bulb is giving off. It's not every, well, I don't know. That's actually a lot of gorgeous colours, isn't it? Shall we point it towards the sun and see if we get something slightly different? And then we'll crack on, because we're nearly at the end of the lesson. You have done a lot of learning, hopefully. It's nearly time for my episode. Where's the sun? I'm not really on the right side of the house, but let's have a go. Rubbish, isn't it? I'll have to trust you to take your own thing outside on a nice sunny day. Oops. I can't even see what you can see. Oh, there we go. Okay. Oh, all right. This is hard to do. And yeah, not very good telly either, is it? I'm trying to angle my camera and angle you as well. You'd think I should just be able to point it upwards, wouldn't you? I think we're. Oh, it's just so infuriating, guys. How much do you just want to be able to get that rainbow in there? Oh, is it there? It's there. I can see it, and even when we see it, it's going to be massively disappointing. Oh, whew. I'm not going to bother. I might try and show you my white computer screen actually, just before we move on, because computer screens and TV screens quite famously only give off 3 colours. I wonder if you can see them. I can't tell you how much better this is if you just use your eyes. I think we probably better. She says, I'm awful. I just, I know, I'll angle it like that, that's better. As soon as I've had an idea, I just really need to finish it. Oh, there we go. Does that look exactly the same as it does before? I think you can hopefully see there that a computer screen is only made of red and green and blue lights. So we've got a little bit of orange. Obviously, there will be some. Oh, in fact, that's because I was holding it over a different bit of the screen, not the white bit. And there will be a bit of sunlight getting in there. There's not really any purple in there, is there? Hopefully you can see that looks different. Anyway. Right. Why are we even doing? We're doing it because this is an incredibly useful way. Well, it's discovered. We use spectroscopy, splitting up light, to see what things are giving off for loads of different things. But it's a really good way of seeing what the atmosphere of exoplanets is, and if they have atmospheres. So here's a good diagram. Thanks again, NASA and ESA and A field, wherever you are. You've got a star here, you've got an exoplanet here, it's got gas all around it. When the starlight travels through the atmosphere, the particles absorb different colours of light. So here we've sort of got a graph which you can imagine that sort of should be a straight line if the planet wasn't there. But this planet has got methane in its atmosphere, and methane has absorbed exactly this colour of light, or this kind of wavelength of light. So you see a dip in the graph. WASP 39b is an exoplanet, about the size of Saturn, 700 light years away. Here's a beautiful photograph of WASP. It's not, is it? It's obviously not a photograph. We can't do that yet. It's a beautiful artist's impression. But here's what you get if this is how humans who are not astronomers think of planets. This is more like how astronomers think of planets. There's just a graph with, here you go, this would be a straight line, but because WASP 39b has got loads of carbon dioxide around it, it's a bit confusing the way they've done it, that it goes up this time. But you can see that there's the carbon dioxide is absorbing exactly that wavelength of light. So they see that bump and they go, oh, there's loads of carbon dioxide around that planet. And there's a little bump here. They found a lot more water vapour than they thought they would on WASP, and they knew it was there because water vapour is absorbing this wavelength of light, so they're seeing less of it. That's amount of light blocked, because I don't know, they've just tried to confuse us. Right, you lot. That is the end of all of the stuff that I wanted you to learn. That's a lot of stuff to learn, wasn't it? So I will explain to you. I said that if anyone was new, I basically busk science lessons into the internet. I'll explain to you how that works so that I can hopefully make some money, because if I can't make money, I can't do this job. And then we'll do the new bingo game that I've come up with, okay? So how it works is, everything that I do is free. I just started streaming lessons in lockdown, sort of for the kicks and Facebook likes. And it just, it went really well. So I'm having a great time and you're enjoying it. So we're just not going to stop, eh? All of my lessons are free. There's this all ages lesson, which is on like a different topic each sort of term. There's an IGCSE physics lesson, and there's a Lego story show, which is like a chat and an activity, and I tell a story with Lego. I store them all on one website for free. There's optional printouts for the lessons, not the Lego show. And I say, if you are using me as a resource, if you think that all of that is worth £5 a month, £5 a month! It's the same as 9 McDonald's chicken nuggets, chums. If you want to pay me the equivalent of £9, 9 chicken nuggets, you can pay me £9 if you like. Go to my website, which is called Coffee, which is where you can support people with small amounts of money. So if you go to my, I think it's in the description of this video, or it's in the About section of YouTube, or if you're on my website and you click sign up, then it's there. Or if you're on my Facebook page and you click the sign up button at the top, then it's there as well. And yeah, sign up support with £5 a month. You can cancel literally anytime you like. If you can't work out to do it, just email. You're not even emailing me now, you're emailing my husband. So you'll just get a reply straight away and he'll sort it out. It's amazing. And I send you nice things to say thank you. I won't go on about it because I want to do the bingo quiz. But if you sign up to support me, if you're watching live, you get the usual past issue of Theatre of Science magazine that I'm currently sending out in my welcome pack, with a home compostable plastic bag so you can grow some mould, because it's all about mould. There's a choose your own adventure. There's a beautiful comic about how penicillin was discovered, and I send you some rainbow glasses as well. Actually, when you just put all that effort in making a spectroscope, you could just use these glasses. They make you see rainbows. But at the moment, everyone's getting a bonus little model of a satellite as well, which is really cool. And some other glasses which make you see other awesome things. So thank you very much if you have received those. That means that my job is partly thanks to you. Could not do this without people paying me. Right, are you ready for the brand new bingo quiz type thing? Here we go. I've got a bingo quiz grid here. Some of you, if you've been to my website, will have got it in front of you, but if you haven't, it doesn't matter. I want you to answer the 6 questions, like scribble out, or I mean, if you haven't got the sheet, maybe you want to just quickly draw 16 boxes. Just do like 3 lines across and 3 lines down. Scribble in the little square that you think is the right answer. And then I want you to tell me at the end, what shape have you made? If you've got all the answers right, you will have the correct shape. So for example, here's how it works, right? Example, if this was your grid and I said, what colour is the grass? Then you would cross out green, yeah? And then if the next question was, what's my name? You would cross out Lara. And if the next question was, what goes on the outside of a sandwich? Then it would be bread. So the answer would be you've made this L shape here. All right, are you ready? Yeah, you are. Let's do this. Okay, first question. True or false? There are more planets than stars in our galaxy. True or false? There are more planets than stars in our galaxy. So from left to right, top to bottom, the things in the boxes are: in our galaxy, artist's impression, brightness, size, Earth, coronagraph, sonograph, spectrum, shape, wobble method, maybe, transit method, photo, true, in our solar system, false. Are there more planets that you picture our Milky Way galaxy with like at least 100 billion stars in it? Are there more planets or not? Okay, next question. I will go through them all again, so don't worry if you made a mistake, you can correct it at the end. Number 2, complete the sentence. An exoplanet is a planet that is not what? An exoplanet is a planet that is not what? In our galaxy? That is not Earth? In our solar system? What do you reckon? I thought it was better to go quite quickly and then repeat them instead of going really slowly through each one, but then that's the only chance you get. So I will move on. What's the nickname for the radial velocity method of finding exoplanets? We've done loads of stuff, by the way, that is on the IGCSE physics astronomy, IGCSE astronomy syllabus. If you ever want to do like a big posh exam in astronomy, this might get you some marks. What's the nickname for the radial velocity method? The method where you've got a planet that is pulling on a star, like the sellotape pulled on our hand. Wobble method, transit method. Okay, next one. What's the name of the thing that blocks... Oh, we went through this so quickly. What's the name of the thing that blocks starlight so you can see exoplanets better? It's this one on the Nancy Grace telescope. Or there will be when it goes into space. What's the name of the thing that blocks starlight so you can see exoplanets better? In our galaxy, artist's impression, brightness, size, Earth, coronagraph, sonograph, spectrum, shape, wobble method, maybe, transit method, photo, true, in our solar system, false. And we're going to move on because you'll see all these again. The transit method looks for changes in a star's what? I think this is quite tricky. The transit method looks for changes in a star's... So you've got a star, you've got a planet moving in front of the star. What does that change about the star? Does it change the spectrum, the brightness, the size, the shape, the photo? Next one, like and subscribe. This is a great something of exoplanet Kepler 62f. Ah, it's such a great one of those. But what is it? That's exoplanet Kepler 62f. But is that an artist's impression or is it a photo? All right, all of those one more time. Question number 1, true or false? There are more planets than stars in our galaxy. There's about 100 to 400 billion stars in our Milky Way galaxy. Are there even more planets than that? Is that true? Can it be true? Complete the sentence. An exoplanet is a planet that is not... is an exoplanet not in our galaxy, not Earth, or not in our solar system? Question number 3. What's the nickname for the radial velocity method, where a planet pulls on a star, so it makes it go to and fro, so it changes the light that is coming from the star, sort of stretches it and squishes it? What's the name of the thing that blocks starlight so you can see exoplanets better? Basically the equivalent of us putting our hand in front of our eyes to block the sun. Oh, just got a new coffee spotter. Oh, thanks. Oh, that's made my day. The transit method looks for changes in a star's... What? The transit method looks for changes in a star's... Oh, that's so nice. Oh, it's like... I feel like I've earned... I mean, obviously loads of you have paid me already, so you've all given me money for this lesson, but that feels cool. The transit method looks for changes in a star's summing, and this is a great something of exoplanet Kepler 62f. But what? Right, should we go through it? Okay. Hello, just popping you back up because I missed you. I should say as well, I haven't said this, I'm so sorry. Over on my Facebook page at the moment is a post saying that if you want to comment on that Facebook post, I will read them out at the end. So there's no comments on YouTube. But yeah, if you're watching live, you can go over to Facebook and say hi, and then I'll go and read it out in a sec. Right, answers then. It is true, yeah, there are more planets because on average there's more than one planet going around each star. So there's so many exoplanets to find. Complete the sentence. An exoplanet is a planet that is not, it's not in our solar system. An exoplanet, Earth isn't an exoplanet, but also Mercury, Venus, Earth, Saturn, and Mars, Jupiter, and all those ones aren't exoplanets. But all of the, there's loads of other stars in our galaxy, and if they've got planets around them, then they would be exoplanets. Okay. What's the nickname for the radial velocity method? That one's the wobble method, where the star is made to wobble to and fro because the planet is pulling on it. So it's like gets squished and stretched. Okay, so it's not the smiley creepy face, is it? Can't be. And it's not the dull oh no, it could be the dull rectangle. Yeah, it can't be the cross and it can't be the creepy face. What's the name of the thing that blocks the starlight? It's a coronagraph. So the Nancy Grace Roman telescope is going to have the first active coronagraph in space that can change. It's going to be so cool. So it's not the dull rectangle, is it? The transit method looks for changes in a star's brightness. That was quite hard. So the spectrum is the colours that it's giving off. A planet moving in front of it doesn't change the colours that it's giving off. It doesn't really change its shape or its size. It changes the brightness, how much light is being given off. And finally, this is a great artist's impression of exoplanet Kepler 62f. It's not a photograph, is it? Because we can't do that yet. Maybe once the Nancy Grace Roman telescope gets up there, we'll see. So it was C. Well done if you got that. And if you didn't get that and you're still here, very well done. You was very well done, because that was, I thought that was quite difficult. A lot of people were saying that was quite difficult on Facebook yesterday. Okay, I'm going to go over to my Facebook page and see if any of you have left me any comments. Hopefully you have. Let's have a look. Press refresh. So yeah, thanks for coming. I don't know if anyone is new. It'd be nice if you were. Obviously, not all of you have Facebook accounts. That's great. That's really good. Don't feed the evil machine. Ah, Facebook are awful. Except they also just like happen to be responsible for kind of all my income. So they're great. I love you, Facebook, but I can see that you're watching. So don't worry if you haven't managed to say hello. I still very much appreciate that number in the corner. Oh, hello. Let's have a look. Who's here? Oh, Arthur's here. His favourite planet is Saturn. No, it's not. Saturn's his second favourite planet, surely. It's a favourite planet. I mean, Arthur, it is really cool, isn't it? Right. Okay, Arthur's favourite planet is Saturn. Morning! Seren would totally name all the bunnies in a field. Totally fair, totally fair. All the moorhen chicks in our local park have names. Whoa. Okay, fair enough. Bad example. Edmund is very interested in exoplanets. I thought you might be an exoplanet person. And he's looking forward to finding out more about them. Well, I hope that you did, Edmund. I hope that you did. Here are some exoplanet top trump cards he made, showing some of the ones that he knows about. Okay, amazing, cool. So I didn't sort of on purpose didn't go into the specific exoplanets. I was hoping that, yeah, I would inspire you to go off and find out about the specific exoplanets if I told. Whoa! Okay, look at this! That's such a cool idea. Top trump cards of exoplanets. Look at that, Proxima Centauri B. That's our closest exoplanet, isn't it? Oh yeah, these are gorgeous. These are beautiful artistic impressions. Really gorgeous, Edmund. Wow. Oh, and you've said what year they're discovered? 2023, 2018, 2016. Their orbital period, nice. How long they take to go around. The radius. Oh, you've measured it in Jupiter's. Yeah, brilliant. The mass, the star distance from the star. So cool. Yeah, there you go. So that's our distance from the star. Proxima from Earth. Sorry, Proxima Centauri is our closest one because it's only 4.2 light years away. It only takes light 4.2 years to get from Proxima Centauri b to Earth, whereas some of these other ones, like Kepler 1668, is over. Wait, no, that says. Does that say 4,000 light years, Edmund, or does that say 4 point something? Does that say 4,000? I don't know. Yes. Right. Let's keep going. Hello, Aurelia. Oh, nice. Is that your toys? I'll open that. Hello, Abba. Hello, Jancy. All right, Jay, Daisy, and Daniel. Hello, you lot. Hello, Ezra and Oren. Hello. Hello, Kai. My favourite planet is Mars. What you just get off me, you lot. Favourite planet is Mars. 2 weeks on Mars. You'd be begging to come back to Earth. You'd be like, I've changed my mind. Hello, Imogen and Ophelia. Hello, Lara and Finlay. It's a good point. Like, I suppose my favourite house isn't my house. Yeah. Hannah and Freya, Lara and Finlay, Imogen and Ophelia. Oh yeah, we're really. Hello, you lot. Hello, Alice. Hello, Lorenzo. Hello, Lauren. My favourite planet, apart from Earth, is Neptune because it's a stormy planet. Nice rainbow. Thank you. Hello, Bella. Excited for the lesson. I found out what musical I'm doing with drama. It's called Just So. Oh, like the Just So stories based on the books that are like how the zebra got its stripes and stuff. The premiere in 2006 had John Barrowman starring. We're learning the audition song this evening. That's exciting. Bella, I am learning to sing. This is my dark secret that I'm not telling anyone about. I would love to be in a musical. I've decided that I've put it on my bucket list. I want to be in a musical, so I'm watching lots of YouTube videos to try and learn how to sing. Like, I can sing in tune. It's not awful. It's totally fine. It's just I can only sing about 8 notes. And if you're in musicals, they sort of need you to sing loads of different notes, don't they? Ugh. So I'm trying to do lots of exercises to like stretch up a bit. Jessica is making a baby dragon puppet. Of course you are. Of course you are. Like, why wouldn't you be doing that? Why aren't you all making baby dragon puppets? Come on, you lot. Here's a big dragon puppet I made. His name is Thorn. Oh, that's a great name. Oh, and Jessica is saying hi to Rose and Aurelia. Okay, I'm opening these tabs. Hello, Jacob. Hello, Sky and Cassie Ray. Hello. Oh, Sky and Ray. Those are excellent names for doing an astronomy lesson. All right, Freya and Arlo, watching in Ireland. Hello. Hello, Lyra and Chippy the cat. Can you do a Lego story show on snow leopards? Yeah, we should. I have done a big cat lesson, a big cat Lego show about snow leopards. So they feature a little bit in the big cat. If you're on YouTube and you go Fit of Science, big cats, then it comes up. I'm wearing an awesome dress. And I gave it to the charity shop and I don't know why. Anyway, so I can't watch it back. It's too upsetting. Hello, Effie and Frank. This is Claw, a land that we have created. Sure. Why wouldn't you create a land? Why haven't I created a land? All right, Levi and Ezekiel. They're enjoying making crafts. I'm laughing because this is a picture. This person is not making a craft. This person is about to hit me in the face with a long paper stick. But you do really look like you're enjoying yourself, so that's good. Seren's name means star in Welsh. Are you kidding me? All right, nice, well done. That's great. That's too late. I've named all my kids. Hello, Isabel and Thomas. Hello, Carly. Thomas's favourite planet is Neptune because his favourite colour is dark blue. Interesting. Here's Scrappy. I made him some new lace bracelets and got him a bandana. All right, let's have a look. And oh yeah, there's Tamara saying nice. Hello, William. Hello, you. Hello, Emma. I'm enjoying my first day of science lesson back in the UK. Oh, nice. Congratulations, I guess. That is good. That's great. Oh, the UK is great. It is nice time of year for the UK, isn't it? The birds are all making their nests. We need to do a Lego show about nest building, actually, because it's just amazing, isn't it? Oh, Wilson is Wilson. Hello, Wilson has been watching with me. Hello. We need snow leopard versus cheetah versus jaguar. My favourite planet is Jupiter. And we need a Lego story on how to survive a zombie apocalypse or on how AI is too dangerous. Yeah, true. Both those things. Yeah. Maybe AI versus the zombie apocalypse. All right, I'll do a quick refresh. And then I'd better go, hadn't I? Because if you're watching live, which you probably are, like, who's watching this recorded? If you're watching live, then in 27 minutes' time, I'm going live again with my Lego story show about colour blindness. He wanted me to learn about colour blindness, and I did it. It was very interesting. It made me realise that I didn't know much about colour blindness, despite weirdly, my dad and my husband, not related, both being colourblind. I didn't realise there's no such thing really as red-green colourblind. Anyway, spoilers. Hello, Emily. Hello. And Elodie. All right, you two. Hello, Sophie and Emily and Katie and Hannah. They managed to make a pastel rainbow that looks like the sunset they saw last night. Hi, Lara. Thanks for the lesson. We didn't do the activity, but it looked cool. I agree. I would name all of the bunnies in a field. And Pluto is a planet. You got the bingo correct. No, you were hoping it would be a rectangle. All right, I'll think about it. Oh, hello, it's Rose typing. So Isabella and Rose saying hi to Jess and Aurelia. Mum loves the wobble method. Really? Your mum loves the wobble method. That's a cool thing to love. That's a cool emotion to have about the wobble method. Right, is that everyone? I think that's everyone. Okay, let's have a look then. I'm just making sure that I haven't missed anyone. Then we'll have a look at some of these images. I've stopped showing images because it takes a long time, and also, like, I don't know. I don't put images of my children, so I'm not sure whether I should be condoning you not being on the internet. But if you've sent me a picture of some stuff, that's all right. Like, is that Scrappy? It's okay for Scrappy to be on the internet. Nice bracelets, dude. Nice. Is that a bandana? That is cool. What's up next? Oh, hello. Oh, it's Claw. It's the world of Claw. Should we turn... Wait, if I unplug my computer, we can turn it sideways. Hashtag technology. Yeah. Whoa, that is cool. I've been to a playground like that. I love it. Oh, my days. That is... What is that? Is that floating? What? Oh, it's a bridge. Is that a floating... Is that like a sky bridge with two... Oh, yeah. Is that mountains? Love the shape of those mountains. Is that roots? Do you like how I'm just asking you loads of questions that you can't answer? That must be really cool and not at all frustrating for you. That's so good. That's great. Oh, I see. Look. Effie's done that side. Frank's done that side. Yes. Did Ruth draw that bit in the middle? Very cool. Very cool. Well done, you lot. I like that. What is even coming next? I don't know. Oh, it's the video. Okay, let's have a look at this video. Whoa, that's good. Wow. Dragon puppet, you see? So that's the adult. Oh, it's been in a scrap, hasn't it? That's really nice. It's very effective, isn't it? I've got a friend, she runs a theatre company called Hogwarts Theatre. She is well into puppets. She would be absolutely all over that. I might share, actually, so that she can steal your idea. And so there we go. Blue, the dogfish, and Mars, the red alien, not red due to eating someone. That's good. That's good. I'm glad you said that. All right, you lot. I'm going to go because I need to set up my Lego story for the Lego story. But thank you so much to the people who have actually signed up to support me while I've been talking. That is a real confidence boost, is that? I'm going to go. I have nothing more to say, except we've got 3 lessons left of astronomy. We've got 3 lessons left, and I kind of wanted to do galaxies and black holes and dark matter and space probes. But we'll see. I'll work something out. But anyway, another astronomy lesson next week. Hope to see you there. Thanks, Hugh, for all your support and all your awesome messages. See you soon. Bye.